Right, in this video we're going to be looking at the ninth question, so question 9 in the June 2018 paper. This is on fluid dynamics, fluid principles. It has to be said, I'm not a particular fan of this question, and that's down to the diagram we've got over here, as it's generally quite misleading for a lot of people. So let's have a look at it. A dam is 8 meters wide. If we have a look at the diagram here, what you can see is a 2D side image, a cross section of the water and the dam itself. Okay, so this information is actually really important. So what I'm going to do is I'm going to quickly draw it out as if it's in 3D. There's no real additional benefit. No additional benefit whatsoever, other than I can now see it as a 3D object. I know what is going on. Okay, it doesn't have to be perfect, just crude one will do. There you are. 3D. Dam is 8 meters wide. So let's talk about this distance here being 8 meters wide. Okay. That sets us up quite nicely for this part 1. Calculate the area of the water against the dam wall. Okay, we're not dealing with the area of this trapezium shape, we're dealing with this area of the rectangle touching the water. Okay, unfortunately it's on the reverse of this dam that I've drawn here. Okay, so you just got to imagine this is slanted, yeah, but there's a front face that has got 6 meters of water in its height and 8 meters across. So in other words, you've got a simple rectangular shape which is 6 meters in height and 8 meters in width. And you've been asked to calculate the area. But we know that for a rectangle, the area of a rectangle is simply times the length by the height. So 8 times by 6 is going to be 48. Don't forget the units being meters squared. And we can call it a day for that one there, 2 marks. Okay, make sure you write your answer on the answer line down here. So not too difficult in terms of its operation, however, the diagram does not particularly help. So by noticing that it's a 2D image, draw it in 3D, allow yourself to have a bit of ease with thinking and get down to the rectangle shapes there. Right, part 2. Part 2 is a follow-on question. Okay, it's going to use some of the information we've had in the first question to help us with this one. Calculate the hydrostatic thrust on the dam wall. Hydrostatic thrust. Well, might not know the formula. Fortunately, I've had this beside me the entire time. Okay, fluid principles. You've got, oh, that lighting is particularly horrendous. Let's see if we can solve that. It's a bit better. Fluid principles have got 4 formulas. You've got continuity of volumetric flow, continuity of mass flow, hydrostatic thrust on an immersed plane surface. Well, that's really useful. Okay, because we do have an immersed surface, alright, and it is flat. And we've got the formula F equals P, G, A, and X. Well, it's not a P, okay, that's a symbol for density, alright, Greek letter. G, we know what G is, okay, it's a value for gravity. A, capital A, should know as area. Area being the area we just calculated a moment ago. And lastly, X. Now, X is this value, this made-up value that does confuse quite a few people. Okay, so let's try and explain it in the best possible way. If I exist in a body of water, let's say I'm at the sea, and I am on the water surface, I do not have any pressure acting on me because I am on the water surface. However, if I go down 10 meters, I will have a body, okay, of 10 meters of whatever the surface area is acting above me, acting as a pressure down on me. Okay. Now, if I'm an immersed body, let's go back to the image. Okay. I've got a small amount of water acting on me over here at the very top, pushing against the wall. It's a small amount. However, as I go down, I get more water. But I've been asked to calculate the hydrostatic thrust. Okay. With that, the thrust acting up here against the wall is going to be a lot lower than the thrust acting down here. But they want the entire wall. So you need to add up the thrust acting over here, in the middle and at the bottom, and find an average. Now the best thing to do for this, okay, is to have this x value, alright, in the formula, this x value. This x value means you take the whole height and you divide it by 2. Okay, the reason for that is that will find you the average along the wall surface, and from there you could then calculate the total thrust acting on the down wall rather than a specific location at the top or the bottom. Okay, the entire thing. So once you've got your formula, it's as simple as just plugging it all in. Let's pop this back down this way. You've got F, which we're trying to figure out, equals the density, or the density is going to be the density of the water. Fortunately for us, they gave us that information, so it's going to be 1,000 kilograms per meter cubed. Also tells us what units we should be using. Gravity, 9.81. Area, 48. Times by this magic x value, which is going to be the height, which was 6 divided by 2. So x is going to equal 6 divided by 2. In other words, it is 3. And we're going to pop that value there on the end. I can't do all of that in my head, so definitely do this on a calculator. Where is the... There we go. We can now see what the calculator is saying. Okay. It was 1,000 times by 9.81 times by 48 times by 3 equals 141264. I believe that says 6. No, that says 0. Apologies, I can't read it when it's in the light. So that's going to be a force equal to 1412640. I'm going to do some rounding here. Let's get that down to 1.41. 413. And I'm going to call that mega newtons. Call it a day there. Okay, so make sure you're placing your answer at the very bottom of the page there. 1.41 mega newtons. You can, by all means, keep your answer as that. Okay, some people may want to readjust and go for that in the form of meganewtons, and that'll be absolutely fine as well. This is entirely your decision. Right, that's it for this video. I'll see you on the next one.